Well, today we are going to see the concept of pressure and the definition of absolute pressure, relative pressure, and what their differences are. In a gas-filled container, pressure arises from molecules' movement and collision with walls. You might think, but molecules are small and they don't cause tiny collisions. However, in a container the size of a Rubik's Cube, which is just under 6 centimeters per side, there are all those molecules. Many. With this, the fluttering against walls is constant, continuous, and ultimately generates homogeneous pressure on all walls. If we consider a container that is loaded with a series of molecules in motion and having a certain pressure, when we lower the piston and decrease the volume, we also decrease the surface area, causing the same molecules to collide with a smaller surface area, thereby resulting in an increase in the pressure exerted by these molecules. When compressing a gas, pressure increases. Moreover, temperature, the friction between molecules, when closer, causes increased rubbing, resulting in temperature rise. Compression involves increased pressure due to reduced volume and temperature due to closer molecule interaction during the process of reducing volume. If we were to position a pressure gauge prior to and after this compression, we would observe that the pressure rises. This pressure concept. Let's see absolute pressure. What does it mean when pressure is absolute? In a tank with 0 bars, negative pressures do not exist when it has been emptied completely. Opposing pressures exist, but they are not negative. If we label a pressure as negative, it is a convention based on the direction of pressures relative to a force. We have opposite pressures, which can be called negative, but they are actually just opposite to the initial pressures. If we have 5 bars versus 3, in the end we'll have 2 bars, okay? But the 3 bars won't be negative, they will be opposite. Well, if we have that tank with 0 bars, with an absolute vacuum, and our pressure gauge is in vacuum, nothing interacts with it. When we connect it, it will measure 0 bars, okay? When loaded, the tank with 5 bars will display 5 bars, as it reflects the pressure at the point of intake. In the void, nothing affects him. That's the concept of absolute pressure, measuring the pressure inside a container. What about relative pressures? The typical procedure is that we will consistently work with a pressure gauge, and that pressure gauge already possesses its molecules applying pressure on it at all times. Think that we are inside an air pool, everything is full of molecules, and we have a bar, okay? We possess a bar that exerts pressure on us. With this, the pressure gauge already has that opposing bar at its tapping point. With this, in the event that we have 0 bars and we charge it up to 5 bars, there will be a contrasting pressure. The pressure gauge will read 5 bars at its inlet and 4 above it, and 1 on it, which is the atmospheric pressure. To mark to 4 due to oppositions against the decision. This is very important because when measuring, we need to know that we are measuring relative pressures. By adding 1, which represents atmospheric pressure, we can calculate the absolute pressure, which is the actual pressure inside the tank. Thus, absolute pressure is gauge pressure plus atmospheric pressure, which is a VAC in this case. Be cautious with the units, as you may come across millimeters of water column, psi, kilopascals. Another topic, conversions of 1 atmosphere in psi and kilopascals, not included in this document. We want clear concepts. Thus, absolute pressure, the actual one inside the tank. Gauge pressure, the one seen on the gauge. And we observe that they are not identical. There exists a distinction, namely atmospheric pressure. If we were to have a pressure gauge in the atmosphere with an open tapping point, it would indicate 1 bar higher above it and 1 bar at the tapping point. 2 opposing pressures that nullify each other, thus resulting in a reading of 0 bars. When a pressure gauge is placed in the atmosphere and is already being pressed by its surrounding air molecules with a certain force, and we puncture it against a completely empty tank, the gauge will indicate a reading of -1 without the need for the previous equation. It is assumed that the gauge pressure is equal to the absolute pressure minus the absolute atmospheric pressure, which is 0 in this case. Atmospheric one, in this case, 1. It is equal to the gauge pressure, which would be 1. Then the pressure gauge will measure 1 bar less. But we have stated that cannot be. Pressures cannot be negative, they can be opposite. Okay? That's why in the pressure gauges on the dial, we have this little dot where we meet with that, a pressure of 0 bars and a pressure of -1. Well, in this case, the pressure gauge measures gauge pressures. So 0 would actually be 1 bar absolute inside the tank, and 1 would be equivalent to 0 absolute bars inside the tank. That's why when we download a machine, we don't stay at 0, but we go down to -1, which is actually when we have 0 bars inside the tank or inside the pipe, in this case. You must exercise caution when dealing with this, as the entry of the refrigerant rule can be in either absolute or relative form, and it is important to note that all of them have a 1 bar offset. Here it is very clear, when we are already at 1 bar, how it starts to vary by 0.8 plus 0.2, reaching 1 bar, so 0.6 plus 0.41 bar. At this point, we start to observe the decrease in absolute pressure and the conversion of gauge pressure to a negative value. In fact, it is recording the atmospheric pressure, which is higher than the tank pressure. They're not negative, they're opposite, okay? When accessing refrigerant tables, we encounter a depiction of the downforce refrigerant regulation on the mobile device. We observe that when we input the values, it prompts us to specify whether it is relative or absolute. This distinction can vary, but in the end it's the same point. Why? This is R134A and we are on the Rossio line. As R134A is an azeotrope, it means it has no glide, which means it evaporates or condenses at a constant temperature. If we have the same temperature inside the bell jar, it means that is equivalent to a constant pressure. With this, saying that the 134A, in this case, is evaporating, condensing, whatever, at that point it is at 39.44 OC. That means it has a relative pressure of 9 bars and an absolute pressure of 10.01 OC, because the atmosphere is actually 1 bar and a little bit, okay? But you have to understand the concept. In the container, absolute, gauge measures relative, and to the relative, to that manometric, add 1 bar, hemispheric side, to no inside tank, okay? Thank you very much, see you in upcoming video.